So today we'll learn about the stress and strain curve. So in the previous class, what we have seen that we have defined what is stress and strain. So in this class, we will study about stress strain curve. So for the stress strain curve is a curve where the strain is plotted in x direction and stress is plotted in y direction. So what is strain? Strain is given by, so here we will consider only longitudinal strain. So the strain in a say wire or a rod. So the strain is given by delta L by L and stress is force per unit area. So for such measurement, what we do, we take a arrangement as we have discussed in the previous class. So this is the arrangement. So this is a reference wire. This is a reference wire where the scale is attached. Now this is the experimental wire. This is experimental wire whose Young's modulus we have estimated. Now what we will do in this experiment, we will produce strain by applying stress in this wire. So for applying the strain will be the longitudinal strain because the stress applied is in one direction. So how we apply the strain? We put masses in this holder. So with the increase of the mass, the stress will increase because the force will increase, and as the area is constant, so the force per unit area will keep on increasing, and as a result of this, the length of the wire will get increased. So this will give the increase by say delta L, then strain will be given by delta L by L. Now say what do we do? We make a table like this. So stress is given by weight per unit area, strain is delta L by L. So for a wire, say this is the length of the wire L. Now when the weight applied is 0, the length of the wire is L. So as we keep on increasing the weight, the length will increase, say by delta L. So using this pointer, we can measure how much is the delta L. For we keep on increasing the mass and the weight will change, and as a result the delta L will change, and for each mass there will be different delta L and hence different delta L by L. That is, for different weight there will be different stress and corresponding strain will be measured. So in this table, say this is for just for an example, say we put a weight of say 1 kg, 2 kg, 3 kg till 10 kg suppose. Then as a result there will be a corresponding stress, and as a result of this stress, strain will be produced delta L by L. So what we will do, we will plot this in y axis and this one is x axis. So suppose if you consider a steel rod or a string, so we will get a graph similar to like this. If we plot for various strain, so we will get like this. Like this. So in this class we will explain different part of this graph. So initially, as you can see, suppose this is the point O. So this is the O point where stress and strain both are 0. Now as we keep increasing the stress, the strain will also increase. Say the stress increase proportionally, the strain increase proportionally with stress till a particular point, say A. This is a point A. Now as you can see, in this region, in OA is a straight line. Fine. So first region is suppose OA. So here the curve is straight line, that is the slope is constant. Now as slope is equal to, yes, slope is stress by strain, so the slope is constant, the stress by strain is also constant, that is stress is proportional to strain. So this is Hooke's law. So this region from O to A, here the Hooke's law is followed, and this point till which the Hooke's law is followed is called the point A, is called limit of Hooke's law. It's called limit of Hooke's law. Now what is the speciality of this region? In this region, as we can see that it is a single slope and the stress is proportional to strain. So slope of OA, the slope of OA, the slope of OA gives the Young's modulus. So we can know the Young's modulus by calculating the slope of this curve. So as the slope of OA gives the Young's modulus, so it gives the elasticity of the material, elasticity of the material. So higher is the slope, if the slope is high, that is steep, then y is high and elasticity is high. So this region. Now another important thing what we can see is that in any point in this OA, in any point in this O to A, if we say here, if we load the wire by giving a stress till this one, we will get a strain of this O to this length, we will get the strain. And if we remove the stress, that is if we unload the wire, that is we remove the weight, what will happen? The length of the wire, the strained wire, that actually was L plus delta L. Now it will again get back to length L, that is the strain is recovered, the strain can be recovered and the wire get back to its original length. So in any point on this will happen. So this is a property of elasticity, that is the OA is within elastic limit. Now say here in this point there is another point called B. So as you can see from A to B, what happens? The slope is changing, that is slope is not constant. So in this from A to B, the slope is changing and it is not constant, hence Hooke's law is not followed. But one thing is that in any point between A to B, as we remove the weight from the wire, if the stress is 0, then strain also becomes 0, that is the wire get back to its original length, Hence, though Hooke's law is not followed, yet the elasticity is there. So B is the limit till which the wire can get back to its original configuration when deformed force are removed. Hence B is called yield point or elastic limit. So B is called elastic limit or yield point. Now, and the corresponding stress, the stress corresponding to B is called yield strength. This is yield strength, that is sigma y, yield strength. So what we see, from A to B, Hooke's law is not followed, but if stress is 0, then strain becomes 0, that is strain can be recovered. So B is called elastic limit or yield point. Yield point because after that the material will yield, that is if we apply more stress beyond this point, then the material cannot recover back to its original length. So also another thing, the stress corresponding to the point B is called yield stress given by sigma y. Now, as you can see, after B, what happens after B? See for O to A, we have seen that for a large variation of stress, there is a small variation of strain. That is, the slope is steep. Slope is steep means dy is more, dx is less. Slope is dy by dx. So for a large change in y, there is small change in x. But see, beyond B, beyond A itself, as you can see, a small change in stress gives a large change in strain. And beyond B also, you can see the same situation, that with a small increase in stress, the strain increases very rapidly. So what happens? This continues till a maximum point called D. So D is a point which is the maximum stress that the material can handle. If we increase the stress beyond this point D, what will happen? The material starts to break, and this point D is called ultimate tensile strength or breaking point. Ultimate tensile strength. So this D is called ultimate tensile strength. So the stress corresponding to D is sigma T, that is ultimate tensile strength is known as. So from B to D, a small change in stress gives large change in strain. Also, stress and strain are not proportional. Now another important point is that, say if you take any point between B and D, say any point between B and D, say C, here is the point C, suppose. Suppose if you take any point C between B and D, what we will see that for any point between B and D, that is C, if we remove, see till B, if we remove the stress, that if the stress is 0, strain is also 0, that the wire get back to its original length when no force is applied. But if when we cross B till D, what happens? That when we remove the weight, when we remove the stress from the wire, then the strain doesn't get removed totally. The wire gets a permanent extension, say L. If we have considered this point here, then the permanent strain produced would be corresponding to this point. So now, as we can see that in this region from B to D, the elasticity is not there, because when we remove the stress, the material cannot get back to its original configuration. So now what we see that this region from O to B is called elastic region, and from B to D it is called plastic region. This region is from B to D, this plastic region. Why it is plastic region? Because when we remove the stress, the wire cannot get back to its original position, and a permanent strain is left with the wire, and this is called permanent set. This material is said to have permanent set. Now this explanation you can very easily get in your textbook. It is well written there. Now a very interesting phenomena happens after D. So what happens after D? Say beyond D, as you can see, if we increase the stress beyond D, what happens? Even if we reduce the stress, the strain keeps on increasing. How it is possible that strain keeps on increasing? Actually what happens, say from D, if we even if we reduce the stress, the strain keep on increasing till the wear or the material breaks at a point F called fracture point. So this F is called fracture point, where the material snaps or breaks into two. Now what happens between D and F? So between DF, between DF, a peculiar phenomena happens that even if we reduce the stress, the strain keeps on increasing. That is, the length of the wear keeps on increasing, and as a result the cross section keeps on reducing till the material breaks. So actually what happens, see, from D to F, from D, you always can get back to this graph. As you can see, even if we reduce the stress, the strain is increasing. Strain increasing means delta L is increasing. So what happens after point D? If we put stress more than the point D, a neck appears in the material. This type of neck appears, and the cross section, because here the area reduces. And even if we remove the even if we reduce the strain, that is reduce the weight, though stress means force by area, so if force is reduced, but area is also reduced, area reduced because of this neck, formation of neck. So stress is not reduced that much, and the necking effect is increased till the wear breaks at point F. So this is the main reason. Even if we reduce the weight, that is, if we reduce the weight, the F is increased, F decreases. So, but here A is also reducing. Here for calculation of stress we are taking this area, but actually the total stress is acting here is increased, and slowly the neck is increasing till it breaks. So the point till which it can bear the stress is point F. So just take a quick review of this graph. So from O to A, it is the from O to A is the limit of Hooke's law. From O to A, Hooke's law is followed. From A to B, though the Hooke's law is not followed, but the material is still elastic, because till B, from O to B, at any point, if we remove the stress, there is a weight, then the material can get back to its original length. But beyond B, say points beyond B, if you take any point, what you will see that the material, when the stress is removed, the material cannot get back to its original position, and a permanent strain is obtained in the material, and the material is said to have a permanent set. Now D is a point where the material can bear the maximum stress, and beyond D the material starts breaking till a point F where the material snaps and breaks into two. So I think this is clear now. Now let us take some example why these graphs are useful. Suppose we are given two graphs, A and B. So for region OA, for this region, say these two region, we can take it M dash. So OM and OM dash in this region. What is the difference between these two? We see that till O to M and O to M dash, the say Hooke's law is followed, but slope of M dash is greater than slope of M. So what the slope gives? Say slope of OM is greater than slope of OM dash is greater than OM. The slope gives the Young's modulus. So Young's modulus of OM dash is greater than Young's modulus of B is greater than Young's modulus of A, material A. So the slope gives the measure of the Young's modulus and hence the strength of the elasticity of the material. So elasticity of B is greater than elasticity of A. Another thing, as you can see here, the D point. So this is the D point, D and D dash, say the highest point, the highest stress a material can take. So this D point determines the strength of the material, the ultimate tensile stress it can bear. So here also you can see that sigma, that is given as ultimate tensile strength, sigma U for B is greater than sigma U of A. That is, strength of B is greater than strength of A. So these two are very important point what we can get from the graph. Another point is, say this is another graph. So this is a point A, point B, point C, point D and point F. Now another graph is given here. This is D. So what is the difference? The difference is that, see, in this graph, say this is graph is for material M and this graph is for material M dash. Now as you can see, in M, DF is large and is larger than DF in M. DF in M dash. So if DF is large, material is ductile, is called ductile, and if df is small, say this one, this is the point D. Immediately after that breaking stress, the fracture point comes, that is df is small, then material is called brittle. So brittle, example, glass is brittle. Ductile, metal are ductile, fine. Or it can ductile or malleable, it is also called malleable, ductile or malleable. So metals, then you may see some region where there is no this region, there is no OA region, only this region, so they are fully plastic. These are like examples are clay, putty, or any plastic. So this is the one important point. Another thing we will see, this region is elastic region, fine, 0 to B. Then B to D is plastic region. D to F, this region is called necking region. Necking because formation of neck. D to F is necking region, fine. So with this we end the discussion of stress strain graph. So in the next session we will discuss about the about the elastic potential energy of a material. Say it can be one dimensional material, three dimensional material, that is energy, potential energy corresponding to longitudinal strain, volumetric strain and shearing strain. I think the strain stress curve is clear for you now.